I'm going to jump into this, and I'm delighted to introduce Mette Ramsgaard Thomsen and welcome you back. Mette was here 2 or 3 years ago. 4 maybe. And we need to use the time because she's jet setting, so she flew in for this talk and she's going to run to the airport after the lecture. And I suppose you're all here because you know that she is the director of CITA, which is the Center of Information Technology and Architecture at the Royal Danish Academy in Copenhagen, at the School of Architecture there. She founded this center in 2005, and that was 1 year after she finished her PhD, which was in computer science and architecture. She did that at the Bartlett, where she also did her diploma in 1996. And that was after having studied at both the École d'Architecture in Paris as much as the Royal Academy in Copenhagen. Her PhD title is, and I quote, Discovering Mixed Realities, Inventing Design Criteria for an Action-Based Mixed Reality. And one of her 2 advisors was Staedelschule's own Sir Peter Cook. So the world is small. CITA today counts perhaps more than a dozen researchers, PhD students. They conduct various research projects, some with year-long grants. And Mette's work with colleagues explores the interface between digital technologies and computation on one side and on the other side material technology and construction systems. It is a very successful center. It's actually expanded. It's taken on a significant international role. It has had support from the Arts and Humanities Research Board, from the Arts Council in England, the Arts Foundation in Copenhagen. And that only adds to Mette having taught at a number of institutions, including Bartlett and the University in Brighton, I think, yes. And also she has been conducting research at research centers such as the Fraunhofer Institute here in Germany, and as much as the Human Interface Technology Lab at the University of Washington in USA. Now, as a sign of all that, the center, as much as Mette, holds numerous prizes, and the most recent one, given in 2016, I believe, she was the first ever architectural researcher to win a Danish prize named the Eliteforsk Prize. And this is awarded every year to 5 outstanding international league researchers who are to enhancing research in Denmark. I had also the privilege and pleasure to see Mette again in Berlin not too long ago in February. And what struck me particularly was that the work seemed to take on a character that I find personally very exciting, where a technologically driven and computationally driven research inquiry into materials and technology actually began to suggest that it unfolds in a larger architectural field and began to sort of tease the potential of introducing a sort of discursive dimension to it. There was that, and if that was not enough, I was then also in Montreal recently, and shining at the reception desk was this beautiful yellow book, big book, called CITA Works, that documents the undertakings that they have had there since 2005. So, Mette, I'm delighted that you have taken the time to join us, and I look very forward to hear your lecture.
Yeah. Thank you very much for the introduction. It's really nice to be here. It's very nice to come. I've prepared a lecture which is a little bit long. Might have to jump in places. And it's very textile focused. And this is because I know Johan being a textile nerd, and I think we have very common interest. I'm going to sort of move in and out of a sort of larger narrative, which is maybe what's the role of textiles in architecture. But of course, what I really am is I'm the head of Sifter. Sifter is the Center for IT and Architecture, and what we look at is computation. So why computation in textiles? I think textiles is a really interesting model for thinking about how we represent, how we design, and how we build architecture. So there's something about the modes of representation that's going on in textiles and the modes of making that's going on in textiles that I have found very interesting. So maybe it's just a particular aperture, it's a particular material practice. What I really enjoy about textiles is it's very, very wide. There are many, many different kinds of practices inside of it, and it's very, very rich. It's very old tradition. There's a huge amount of knowledge embedded into it. So maybe that's a sort of point of departure. What we look at in Sifter is how computers are changing the way we think, design, and build architecture. And thinking part is really important. Often our field becomes very technological, very much about sort of optimization. We are given tools like this. We're shown BIM as a sort of paradigm of just bettering the existing practices. But I believe that there's much more at stake. For me to see, we have entered a new realm of representation, and we're standing at the cusp of something that is just as important as the invention of perspective. So in a way we have entered. Do you want me to go closer, or? Okay, you decide. It's a little bit distracting. But we have entered a sort of period of reinvention of our practice, which I'm personally very excited by. We work in a practice-based research method. We build a lot of one-to-one installations, demonstrators, and this is really through an idea of that technology is something we make rather than technology is something we use. So I believe very much that architects are particularly prone and good at being given a tool and immediately breaking it and finding the edges of it and deciding to misuse it. And I think the only way you can enter those practices is by doing. And so the making practice in Sifter has been fundamental to our sort of evolution. We teach, we do a lot of workshops. In these workshops, we teach the way we research, so we embed students in the same kind of way of our own practice. And we develop questions. Sometimes the questions are questions we don't know, like, could knitting be an interesting paradigm for architecture? I did a workshop with that for 10 years ago, and I've been working with that ever since. But it started as a workshop. And sometimes it's the other way around. I come with a mature research project, and I open it up for students, and I see how students might navigate the same sort of territory of concepts and tools and ideas. We also have a master's program, which I won't pitch here. So anyway, I've a little bit repetitive from the chat in Berlin, but maybe it's a point of departure. Why this interest in textiles and architecture? And of course you could say, well, there are two central traditions, maybe the tent and the tapestry. The tent as the textile as a constructive membrane, structural skin, and the tapestry as that which lines the space and encultures the space. And these two traditions, I think, are very interesting. We could think of the new tent, new, but still the new tent. How could the tent be constructed today? And perhaps also the new curtain. And obviously we have excellent practitioners working with these ideas around us. For me to see a very important interest in textiles is this idea of the tapestry. So this project, which is ongoing, but maybe I started 6 years ago, started with a trip to the library, in which I went to the library. I wanted to work with an idea of textile history in architecture, and I thought, oh, I'll just go and find a book which says where I can see all these textiles. And I opened all the books, and I realized, obviously, when I look at Villa Rotonda or Villa Medici or so on, they're empty. There is no evidence of any inhabitation. And of course I knew this, but I had somehow forgotten that the life of buildings and the life of how we experience architecture is eroded from our architectural history. So in my own little way, I've been trying to construct a history of textiles and architecture, and be enjoying to think about textiles as a particular narrative in an architectural history, which is somehow parallel but also introducing other kinds of ideas. So textiles has enormous importance in architecture, and if we think of a building culture which is quite rough, these sort of stacking stones on top of each other, a bit of mud, then maybe a textile lining is a nice way of inhabiting space. And if we look at Renaissance pictures, then these silk linings or wool or tapestries are ways that they inhabit. But what's exciting about them is that they are also part of a larger narrative, and they hold stories inside of them. They are pictures, they depict narratives. Textiles are transportable. In the Renaissance, when kings would travel from castle to castle, they brought everything with them. So they brought their court with them, which could be like 30,000 people. They brought their furniture with them. They brought their cooks with them. They brought their cows with them. And they brought their rooms with them. And their rooms were textile. So they bring with them the actual space, which of course is the place that they are held into honor. No? So the place, the moment of royalty, which happens through the crown and the decoration and so on, is actually what's constructed in the textile. So textiles had a huge social economic power. Henry VIII had a collection of 2,000 tapestries, and they would melt down these tapestries and get the gold out of them and reconstruct them. So it's a really just absolutely different way. He was using the major part of his proto-national product on textiles. Today that seems absurd. Then they are rich, they are full of narrative and pattern, they're gilded, they're bejeweled, they're strong storytelling devices that can narrate other narratives of history, and they're political. Napoleon very cleverly used the idea of the empire style, so the journey to the Orient, coming back from Egypt and bringing with him this new style where papyrus, flowers and sphinxes and so on were brought into this structure. This is Notre Dame, where he was the coroned, he was became emperor. And Percier and Fontaine, who were his interior architects, redecorated the cathedral, which is a Gothic cathedral, into this new style. So it's like he can just wash away the old regime and construct his own regime, his own political agenda, and reconstruct space to suit his narrative. They're exotic and scenographic. Schinkel is a really interesting person for thinking about textiles, because with his tradition of thinking about these very large textiles, Schinkel actually visited the coronation in Paris and was very aware of Percier and Fontaine's work. And when he did these textile rooms, which we know are now very famous now, for Humboldt in Schloss Charlottenhof and Princess or Queen Louise, then Napoleon had slept in her bed. He invaded Berlin, slept in her bed, and when she came back, she thought, maybe I need some redecoration. I just think that's so, if I'm going to invade a country, I'm going to sleep in the Queen's bed too. Yeah, it's fantastic. Anyway, so he constructs it as a sort of scenography that we can live in, where we can construct ourselves and our own identity within these spaces. So with me into these more technological studies that I will show now, is this depth of history and depth of architectural thinking this idea of a transformative space, an architecture which is fluid, that you can bring with you from place to place, and which is rich with narrative and meaning in ways that we don't normally think of architecture when we think of architecture as artifact. So it's this idea that I want to bring with me into these more architectural studies, or technological studies. So I've structured the talk around these 4 ideas. Textiles as a model for architecture, the idea of a textile room, digital crafting, material design, and complex modeling. And we'll get more and more computational as we go down, just to sort of proceed it. So, okay. Videos, I forgot to check this one video, but so this is what came out of that workshop with the students, when we just borrowed some knitting machines from the design school and started knitting these studies. And what we were looking at was really I'm going to try to find that video. This is quite fun. Sorry, maybe. No, that's okay. Forget about it. What we were trying to think about was really thinking of textiles not as necessarily a building material, but more as a modeling material. So when we build as architectural students, we build in cardboard and sometimes we cast, but mainly out of planar materials. And architecture is made out of predominantly planar materials. Knit is inherently three-dimensional. We can knit into shape three-dimensionally. We can make hyperbolic surfaces where there's more surface than like a lettuce leaf, there's more surface than there is in the plane. Or we can knit three-dimensionally. So I was asking with the students, how could we use these techniques to imagine other kinds of architectures? There's a mathematician called Dr. Osinga, who has been very famous in using crochet as a way of understanding mathematical models. So there's also a woman called Margaret Wertheim, who's also working with crochet in the same way. So it's sort of along a set of ideas, a set of practitioners working with this. This led to a pretty straightforward project, which was, could we knit a wall? I got some funding from a guy who had built a lot of offices in the 70s, and he knew Hessian walls. Remember Hessian walls? When you slammed the door, then the wall would stand and move. And so he wasn't so shocked by the idea. And here we were together with Manchester University, knitting these very thick spacer fabrics and constructing them as walls. So what kind of modeling tools would we need to develop to be able to create sort of soft walls? And why would they be practical? Well, if they were an alternative to plasterboards, then it's very practical. Rather than having these very big boards, you could sort of roll up your wall, you could construct a framework, and you could clip it on. And within it, you could embed a lot of other functionalities, such as insulation or conductivity or so on. So we were looking at how to specify how we would actually make these walls, and then how to shape them also. How do we make three-dimensional surfaces? How do we generate the cutting patterns? How can we then actually sew them together? How are they relating to a frame? And it's a little bit like sewing a glove. It's absolutely fitted to the hand, and it turned out to be like millimeter precise. And didn't at all have the sort of textile sort of just pull a bit and then so these sort of questions became very interesting, and with it we were working on these very interesting CAD/CAM knitting machines that I'll show you a few times. Right after that we won this competition for an interactive show in in London, and we said very bravely, we said, well, we can do this, but it will move, and it will be 13 meters long, and we'll do it in 3 weeks. And we wasn't really completely aware of the complexity of it, but the idea was a little bit like setting it like idea was that it would move, but at the pace of architecture. So I've been working a lot with sort of actuation and thinking about what would the temporal pace of a building be if a building was an organism. So maybe more connected to the pace of a glacier or a frozen lake, then these sort of time frames are sort of beneath our own experience. While we have an understanding of them, then we can't just, they're not animate. So I got these guys in India actually to make me these fantastic geared motors, which had very little power in them, but were geared down to have a lot of torque. And a little bit like a sort of medieval piece of technology. It has these sort of weird arms underneath it that are very basically just moving up and down, but because of the joints system, then it becomes a complex movement. And when we had finished the actual construction, then we switched it on, and then it didn't work. And it was at 4 o'clock in the morning, and the opening was next day, and we just thought, fuck. And then we thought, okay, there's nothing to do, we have to lie. We'll just say it works. Okay, went home and slept a little bit, and then I thought it works, because I had coded all the motors, and I had been planning, and I knew that it was working. I knew they were moving. So I crawled in under this thing into this place here, and then I saw it is moving. And it is simply because when you're looking at the motors, and when you have a rigid architecture, then you can see the sort of clock, like a clock. You can see the arms moving against each other. But when you're looking at this kind of architecture, with this hyper-voluptuous skin, then we have no registration. So here I was imagining, how could an architecture be if it was an organism? What would its movement languages be? And here it was pointing right back at me, saying, what kind of organism are you? What can you even perceive? And I thought that was an interesting dialogue, I think it's called. I've never given the lecture in this order, so it's kind of funny to do it. But I've since then worked continuously with a series of projects I call the Curtin Projects, and they've actually been relatively sort of extracurricular. I do them sort of on the side. They don't fit into the larger narrative. This is the first time I sort of put them in right up front. And I've always wondered really why I did them. And I think that they are much more related to this sort of narrative of the textile room than they are really to the technological examinations. They have a lot of technique inside of them. This is a curtain we built for the architecture house. It's using three-dimensional, we are 3D modeling the surface. It has these suction cups, and it's made in dip-dyed silk. And very playfully you can sort of rearrange it, and you can reposition it on the wall when you draw the curtain. It's a little bit like taking off your jacket and hanging it on the wall. So we were thinking about glass houses and how it is to live in all these houses in Denmark, the north. It's super fashionable to live in these floor-to-ceiling glass house facade buildings. And people live in them very differently than you would do in a normal building, and the relationship to privacy is changing. But one of the things you see mostly is a fantastic display of different kinds of curtains when you go see these buildings. So we were wondering, what do you actually want from your curtain? You want maybe privacy, so the curtain shouldn't be up, it should be down. And so how could you sort of invent that? So here we were sort of, it's also about 3D modeling and pattern cutting and dyeing techniques and so on, but it's also just about how do we reinvent the playfulness of Schinkel's rooms into a sort of modern context. A little bit of making. Here it was also, along with it, we did these studies which were into origami, where we folded the textiles and then created laser cut shibori forms. You know, the Japanese dyeing technique of shibori, where you're binding the textile with blocks and you're dipping it, and then the textile, the water actually only goes in to the edge of the textile, creating these very interesting patterns. So we found ways of developing this, and then laser cutting the forms and laser cutting the textiles, and sort of enjoying the sort of dialogues between what was very sort of well, there is a technique, the technique of shibori and the techniques of 3D modeling and the techniques of laser cutting. Or here in blush, which also has a very technological study. It looks at, again, 3D modeling flounces. So it's a tablecloth for a very, very complex table. The table has several layers, and the tablecloth sort of weaves in and out. And then it uses placed patterns, so digital printing of these silk surfaces, in which placed pattern is in fashion, where instead of just striping the textile, you stripe it in relationship to the body, and you use digital printing to be able to make the patterns. There's a picture here. You can see how the patterns are strategically colored. So that within these very deep silk flounces, then the color becomes really, really vibrant, but on the outside it becomes it's very sort of not pronounced. So this sort of dialogue again between what are you doing when something is flat and what are you doing when something is three-dimensional, and how do you bring these languages together is what's at stake here. But again, this narrative around how can the textile enrich a space and enrich idea of habitation. So going from these ideas, then in parallel with this, there's also a set of projects which are looking at, again, coming from the sort of very banal question of could we make a textile wall where we used a sort of egg crate substructure. Of course we knew it's a very stupid way of building a substructure, and we could use a much more textile-based system where we're using friction between members to develop the subframe. So active bending is a very important term in our field. You could say it's, if I'm from the north, then I would say, well, the idea of using material performance and the bendability of materials is part of my traditions, is also, if anyone is in doubt. But if I came from another part of the world, then I would just have another reference. So it's not like it's foreign to it. But in Thicket and Thaw, what we were looking at here is really trying to understand how we could make the subframe also textile. So here, very simply, bending the wood, tracing the wood, and using this as sort of min and max parameters for a parametric model by which we can then design this sort of structure. So we named this kind of thinking digital crafting because it holds the craft techniques and then the computational techniques, and it brings these worlds together. We did it again for the Triennale in 2010, where we built it in 10 meters high. It was really fun because 10 meters it suddenly starts becoming not just the interior, but something that speaks back to you as a building. A little bit of digital fabrication. But what was also interesting in it was that when we were making the model, then we understood, okay, I'm parametrically designing the single curvature of the beam, and I understand how it's moving, and I understand that if I flex it more, it will break, and if it's less, then I'm not using the stiffness that I'm gaining from the elastic behavior. But we also understood there's something happening in aggregate behavior. So a little bit like building a fence, that when you have many members that are all able to bend, then the structure itself also has its own behavior, which isn't sort of, it's more than, or it's accumulative of the many behaviors of its members. Let's see if this. Yes. So here, and this is whatever, 5-6 years ago, we were using Nucleus engine in Maya to simulate the behavior of the material. So in our field, this has really changed a lot with Kangaroo, which came after this. That there's just a lot of different modeling techniques now to model it. But what we were trying to understand, well, what is the sort of movement and behavior of the whole of the structure and not just of the single beam? And how do we integrate simulation into the design chain, which is a much larger question. So what kind of material simulations do we need to develop to be able to actually think about what kinds of structures we can create in this way? At the same time with this, a little bit in line with strange metabolisms, I was drawing these sets of drawings, which was really trying to project, well, what is this? What would it be like to live in this space? So these drawings were part of the Biennale project also, and what we're looking at here is just trying to understand, well, what's the identity and nature of this space? What kind of language are we establishing, as well as a technological construct? In Dermoid, inherits a lot of these ideas. Dermoid was done with Mark Burry from SAIL, it's a collaboration between the two centers. What we were looking at here is how we could use short members, so wood becomes more expensive the longer it is, so how we could use short members to make large spans. So here we're using just ordinary plates of ply, 2 by 120 by 240, and cutting them and then weaving them together in a reciprocal truss frame system. So reciprocal truss frame is a Japanese structural system where you're sort of leaning members on each other. You can imagine that 3 people can sort of sit on each other's lap, and so you have this sort of system that's working with gravity. So this is not a proper reciprocal system because we're lifting it out of the plane of gravity, and you can imagine what's happening with those people. That doesn't work, no? But it still has this woven logic of these members being brought together. And each member is sipped together with I always forget this, there's a web and a flange, no? Yes, web and flange are then sipped together in a friction-based tie. So what's happening here is there's no glue at all. The whole thing is just brought together like this. And because of the bending, then the thing locks. There's a very simple construction. And it's a way in a space frame, sort of spatialized members that are then brought together. Again, we sort of invented these first steps into thinking about what would simulation integrated design method be. Here again with Nucleus Engine and Maya, just modeling a sort of inflated bubble that would just then reconstruct the topology. Oh, I took those pictures out. Anyway, so that's how it was. When we did it again, we often do our projects many times. We did it again for the Copenhagen Design Week, where we built it for the Design Museum in Copenhagen. And here we then started to look at how could we integrate FE. So FE is finite element analysis, and it's a way of calculating structural strength. And what we were doing here is trying to understand the performance of the structure and testing it, and then building a full model of them and understanding how the deflection of the model was. Well, when we built it again at RMIT in Melbourne, we then also modeled the full structure as a whole in FE and understood the performance of that. So these sort of understandings of lightweight and heavyweight simulation and bringing these together, not necessarily modeling the whole thing using heavyweight FE, but rather interfacing between smarter, lighter weight simulation types that are more spring-based and then more hardcore integrations. At the end, we sort of 3D scanned it, and then we correlated the two scans by putting them on top of each other. You can kind of see it over here. And then we could see, well, what was the simulation is about constructing an expectation of performance, and then the actual 3D scan is what it was doing, and then we could see where are the moments where these things are not, where are the moments where we're deflecting a lot, and where are the moments where we have very good understanding of structural properties. The last project in this series is a project that I did for the Architect's House. You can see the curtain, the other curtain behind. But here what we were doing is really trying to understand the systems that we were working with in Thicket and Thor, and then bringing them together into this sort of textile curtain. So inspired by other textile systems such as weave or knit or crochet, I was very interested in that these representations that we know from textiles, they are diagrammatic. They are not representational, or they're not image-based. When you're looking at the diagram, the knitting instruction. You're looking at an instruction, you're not looking at a picture of how the textile will work in the end. And I was thinking, or I'm very interested in how we can use these sort of concepts of representation and merge them with our own. So in shadow play, what we're looking at here is also trying to understand how these representations can be developed. So here we invented this sort of strange three-dimensional weave system. It's a set of loops. It's set on these bars. The loops are moving downwards and they're crossing in over each other. So they make a 3D textile in wood. At the same time, what we were very interested in is exactly these drawings here. So how can you represent a material system? So if architecture moves from the design of artifacts to also include the design of materials, we need to start thinking about what are the design protocols by which we can understand and develop these materials. And this is in a sort of crude super scale because the stitches of my 3D textile are this scale here. And so it becomes a sort of, it is a diagrammatic project. And what's interesting is that we are now working with a set of tools which are actually inheriting a lot of the logics from these sort of much more early sketches around trying to understand what our representations need to convey in order to be able to develop materials. So yeah, it's a little bit of how did we do it, cutting up slats. Big interest in copper ties. The whole thing was tied together with these copper ties which reflected the light and warmed it, and a bit of design. So this question about how we become, or what happens when the architect becomes interested and engaged in the material scale has been really important for us. Of course, you can say that digital fabrication tools, they're not really bringing something new to the field, no? A CNC machine or CNC milling machine is just a milling machine with the computer stuck onto it. Maybe laser cutting is a little bit new, but it's not so new from cutting. So it's not really the tools that are new, it's just the level of address that's new. The idea that we can bring in a whole new degree of complexity. That maybe if you were some sort of Japanese master builder and you had 20 years to do something, you could also reach this complexity. But in our building culture around us, we rarely touch material in this way. So, of course, if we look around us in the field, there you have 3D sails, or north sails, is this idea that you could make materials that were optimized for a particular use. So you could have a set of tools, you would have simulation of wind loads, you would have simulation of performance, and to that you would be able to build a particular material that is structured in that way that it would work. And now I'm talking as if I'm assuming you know what this is. Do you know what this is? No. So what it is a 3D sail. It's woven on these huge, you can kind of see it up here, on these huge robotic tables that they can level so that they are exactly in the three-dimensional shape of how they expect the sail should be set. And then they laminate with this robotic head, you can see here, across the surface, and they make a material which is directly linked to the particular impact that they're expecting on the boat. So it's a sort of hyper-performance sail made for like America's Cup or something. So you could say in architecture, it's maybe why would we build like this? But I think as we get into a culture which is much more aware of the economies of fabrication and the economies of transportation, this idea of a lighter building culture is definitely something we are going to be working much more readily with. And then the sort of quip of Bucky Fuller, "Madam, how much does your building weigh?" takes on a new meaning. He didn't mean that when he said it, but it's still a very, very relevant question for our time. So this idea that materials could change properties, could grade, and could change according to site or use, I think is really inspiring. in Listener, we looked at this, we came back because it was sort of follow-up of the knitting projects, and here we're working with CNC knitting machines. It's a collaboration with Ayelet Cormont at Shankar University, and we were looking at sort of actuated surfaces, so sort of smart textiles territory, where in bed you can see the sort of gray threads here. There's these sort of silver-coated yarns inside of it. It's made out of 3 different textiles. The white textiles, Dyneema, it's very, very strong, very non-stretchy textile, made for making ropes for ships. Then there's the Lycra, which is the blue, which is of course very able to stretch. And then the silver-coated textile, or yarn which allows the conductivity. So now it's going to work. Yes. So when you put your hand over it, you're changing the charge around a magnetic field, and that's sort of like a dot matrix. It's then locally inflating the surface underneath it. So you could say, okay, this project in one level is about smart textiles and how we could appropriate smart textiles in our built environment. But much more importantly, it became about how to interface the stall machine directly from the CAD environment. Bit of making. So we drew these diagrams. And the diagrams are setting the relationship between a cell matrix, which is then allowing us to construct the actual code that runs the knitting machine. So every point, every cross point in this diagram is generating a new set of information that generates each of these changes between the commas in the code. So what's exciting for me in this project is that we're able to directly bridge between architectural design environment and an environment for materialization. So we've done this several times since then. We have different interfaces, sometimes more TIFF interface where we're building pixel-based images, and sometimes these codes and so on. So and sometimes with Simasheki and sometimes with Stoll. But this idea of being able to directly design the materials and knit them, sort of like printing them, is really interesting. Yeah, so you can see there's a lot of information passing. In Smart Geometry in 2011, we brought these ideas with us, and we looked at how we could test these materials and try to instigate a new kind of design chain. So rather than being interested in smart textiles and actuation, the interest was how can we use the surface to gather information about its environment and then feed it back into the design chain to then make the right kind of textile. So how do we use it for material specification rather than for actuation? Never learned that. So here we have sort of strange feedback chains between prototypical materials and then more realized materials or sort of final materials at the end. This was brought together to Sifter, which we just finished this spring, which is a curtain again for the same house here, but where we looked at making, again, using the sensors, here light sensors from an environment to generate a site-specific pattern or a curtain that sifts in the light specifically according to the light input. So we're generating, again, these sort of huge data sheets which are made from every green little cross is a light sensor, which brings in different kind. We made a reading of 8 hours on one day. That could have been better, but just to prototype it. And here you can see the sort of diagrams of each of the sensors, or sensor fields. What are they reading? And then we calculated that we use standard deviation as a way of calculating difference rather than average, to then understand how we could use these sensor inputs to distribute material across the surface to be able to create a curtain that drew light in where it was dark and was more dense where it was light. So again, it has this sort of diagram as this interface. And here I've inverted the pictures, so this photo is the same as this one, but here it's very, very hard to see it. So when I invert it, you can see the reading of where the material is more loose and where it is more dense, according to the sensor feedback. So this whole idea about what are these new material practices? How do we design with them? And how could we think about, how do we inform material practice, I think is really interesting. Simulation is one way, no? We can simulate how materials work, we can get knowledge about it, and we can start designing materials smarter. But sensing is another way. So sensing is understanding particular local environment, whether it's a material, within a material or within an environment, and then bringing that information into to be able to make material specifications. Here, this is a little experiment we did with Assam Khan in Copenhagen. He's the researcher at Autodesk, where we embedded, so these are sort of fiberglass tapes, and then we embed little pressure sensors. They're just actually carbon fiber, and then they are, if you bend it, there's more pressure on, so they're more conductive. And then they're less conductive. So we can sort of read how the material is moving as we are, as it's actively bending in the construction. So here we are baking our own element in a sort of t-shirt heat press to then actually interface it with the 3D environment. I think what's interesting about this is right now they're prototypical processes and they're very sort of a little bit far-fetched and they're separate. But the point is that they should be brought together. So we should be doing design that has simulation integrated into it, and we should be using sensors within the environment and within the materials to inform those simulations. That's my sort of end game on that one. I'm just going to skip a little bit in the interest of keeping everyone on their toes. So the last set of projects I want to show I'm calling complex modeling. So complex modeling is a larger project that we've been working on for the last 3 years, and we will be working on for a year more, which looks at this relationship between material design and structural design. So if we are right now, as a practice, really good at understanding what's going on at a structural level, also really good at understanding what's going on at a material level, we're not very good at understanding the relationship between the two. So this is a phenomenon called multiscale modeling. Multiscale modeling is an interdisciplinary research topic. Economists, sociologists, meteorologists, material scientists, mathematicians are working with this idea of having many different models that are then interfaced. So you have a large model that is being parametricized and understood by a small model. You have a small phenomena, a little area of a landscape. You model that, and you extrapolate data from that, and you parametricize the large model. So normally, the mesoscale, the scale in between, is an abstraction. It's something that you put into place to be able to interface the two. But in our field, and I guess any design field, but especially architecture, it's very, very rich. We know a lot about the intermediate scale because the intermediate scale is detailing. And we, as architects, know on our backbone that the way we work with materials fundamentally changes their performances. So rather than being sort of an abstraction, it becomes a very, very rich territory, and I think that's very exciting. So in this we have been working, there's 6 projects altogether in the project, and we're doing the last 3 now. The first 3 are here. And what we're trying to do here is trying to understand Well, if all the projects until now has really been about, okay, there's a material practice and how do you use computational modeling to understand or enrich that material practice, then what we tried to do in this project is sort of turn the question upside down and say, well, if we start from computational, if you start from representation, what kind of representations do we need to set into place to be able to work with materials very smarter? So in a way, the project's very similar, but for us, they're sort of the other way around. This is the RISE, which we built for the EDF Foundation in 2013. It is a little bit different from the other projects. The other projects always try to be like a cantilever or a wall, or, you know, they relate to something. But here it's like a bush. It's just a big sort of mass of material. And what we were looking at is if we were going to look at computational modeling, at sort of advanced computational modeling, we wanted to start with something we knew was very tractable. So we started with growth algorithms. And what we looked at here is understanding how a building might grow, or how could we think of a material system as growing. So what's the problem with parametric modeling is that we don't know all the parameters from the start. The parametric model wants us to be able to preset all of these things. And so all parametric models are a complete mess, because as we discover things during the design phase, parameters are added, and that makes it, you know, it makes it a very messy process where it should be very rational. But if we could think of growing our models, so not our architecture, but growing our models, then maybe this idea of the arrival of the new could be encapsulated by these kinds of, by this sort of ability to adapt and change. So we looked at leaf venation, so the way that the leaf grows ores inside of it. And it turns out that these are set by hormones. So there are hormones out in the leaf that then draw the leaf venation towards them. And we use this as a sort of concept for the model. And here we had then a set of tropisms. So like the plant knows not to grow downwards, it grows upwards. It has a knowledge about its environment. Phototropism, that plants grow towards the sun. And thigmotropism, that some plants grow and attach themselves to their environment. So we invented these three tropisms as guidelines in our model, to then be able to construct a model in itself that also had the ability to grow. And in difference to plants, it can also fuse. So it's not just branches, 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 but the branches can meet and become one. The project's built of rattan. Rattan's very fashionable now, but I didn't know it when we started this project. It's a material which is very fibrous. It's a wood, like a liane. And it is made out of these like straws, so it's very, very bendable, yet very, very strong in that direction. It's traditionally made to make furniture. And then we had this idea of bundling, so a little bit like the fibers in the tree, that they are bundles of fibers. We would make bundles of rattan elements that are brought together. So I'll just show you the model again. So with an artificial sun, which was just a point, we then grew these structures. They're growing and finding their way and relating to the environment, shooting off branches that can thigmotropy, join to the building, and also having an understanding of self-weight and the necessity to shoot off branches that construct support underneath of them. As you can see, they're also joining to each other. So it's kind of growing this structure all together. In the first phase, it grows the structure. In the second phase, it then develops the actual fabrication. And you can't see that now. It's beautiful. Anyway, it's, yeah, let's see a bit now. So it sort of grows the actual material specification of all the joints and systems of these bundles. Yeah. So in many ways, the rise is an abstraction. It's not really architectural. It doesn't really want to construct an architecture. But at the same time, it's very much the invention of a new kind of material system that tries to use another way, another logic of assembly and specification. In Learning to be a Vault, I'll go a bit fast over it, but it was David Stasiak and myself that did it. It looks at machine learning. So machine learning, I don't know how many of you know what machine learning is, sort of the paradigm for understanding big data. And it is the cutting edge of how we're going to work with all this data that we get from Google and whatever. So it's a very important paradigm. And in my time in computation and architecture, I've seen at least 3 or 4 sort of rises where people did the great project on machine learning and then everyone forgot about it again and then everyone jumps on it again. And the point is that it's an analytical tool, it's not generative. So it's very good at understanding a lot of data and being able to analyze it and categorize it, but it doesn't have any generative mechanism in it. But it's a very, very interesting set of algorithms around it. What we were doing in Learning to be a Vault is really just to try to understand what kind of algorithms are out there and how can we actually include them into design. So what we did in this project, we collaborated with IAC and with the students at IAC. We got them to build a huge amount of Rotom models. So we gave them criteria, we gave them a site, which was a plate of wood, and they could construct these Rotom models. And then we made a digital model and generated 2,000 models out of it. So we're using genetic algorithm to be able to develop all these models. And then we use machine learning to categorize them. So we just have a huge cluster of 2,000 models. And what do we do with it? So then we found a way of using k-means clustering to be able to use unsupervised learning to actually understand. If you looked in the columns, you can see that they have similarities. Some of them are more vault-like, some of them are more dome-like. There are sort of stories that are appearing. And this is done in an unsupervised way, so there's no top-down. It's just out of understanding a series of parameters and then clustering them along a series. I think we had sort of like something like 14 different clusters or something like that. So I think this is really interesting also as just an intuitive architect, because when we design, we always are aware of that the design space is very large and that my capacity as an architect is I can only move in that design space within a given territory because I just don't have the capacity to understand the whole of the space. So I think machine learning is an interesting way of trying to be able to navigate a larger territory and be able to see all these different variances. And we could very easily be able to sort of say, okay, we're just not interested in that family, but we're interested in that family. So we can much easier visualize and navigate the design space. Right, a little bit of how it actually works. And then we build one in one-to-one. So I don't know how I'm doing for time. I have 2 more projects if you want to see. Yeah? Are you very tired? Should I show one more? You up for it? Yeah? You're allowed to say no. So the second project in complex modeling is Tower, and here again it returns to textiles and knitting, but more to the story of the tent rather than the story of the lined interior or the tapestry. And here what we were looking at is really sort of hybrid structure which allows us to reinforce a membrane structure. So if you sort of imagine that we're using the active bent fiberglass rods, a little bit like the rattan, and bending that, and then stretching a canvas over it, but also tensing the textile so that the textile also has a performative. It's not just cladding, but it's also in a tensile system. what we're looking at here, we started with a series of interest in distributed systems, but ended up in something which was much more globally oriented. So it's a little bit like a pop-up tent. Now you have the rods and you have the textile, and you know that when you can throw them out and they sort of pop up themselves. That's because the relationship between the performance of the active bent rod and the textile is in balance. So what was interesting for us is that when we're working with integrating simulation, then in fact we only have really two systems. We can simulate very well things that are either in tension only or in compression only, but it's very hard to do things that are interacting between the two. And so our aim for the project has been to develop a design tool in which we can have more than one material performance and understand their interaction between them. So a sort of design aim was to build a 10-meter high tower outside that was going to bend in the wind. I don't know who invented this. It was a very, very difficult design ambition, but that's what we said we wanted to do. So we had this idea of a resilient tower that could sort of bend and deflect and then sort of recuperate actively. And as a complex modeling project, we're designing at multiple levels at the same time. We're designing the structure, we're designing the fabric, and we're also designing the relationship between the element of the rod and the textile system. So we're sort of engaged in all the levels of designing. Just keep it a little bit shorter here. Sorry. That's a bit too fast. Here we go. I never understood video and restarting in PDFs. Yeah. I might just restart the. Sorry, guys. Yay! So what it's doing is, you see you're simulating the bending of the beams, and you can see these little lines, they're sort of indicating the extrema of the beams. And then we put on the surface, and we can also simulate the relationship between the knitted membrane and the actual bending of the beam. And then it's a sort of multi-story system which is built up. But so what's exciting for us in it, it really doesn't want to play with me at all, this thing, is really to try to understand that normally when we build membrane architecture, actually the making of the seams is not at all an architectural concern. It's done by the engineers. And of course, it's incredibly important for the look and feel of something. So we were interested in being able to design both the membrane, both the cutting patterns of them, but also structurally design them so we understood what the performances of them were. So here we then invented our own relaxation algorithms to be able to understand the planarization of them. And here we're testing them, 3D scanning them and understanding the relationship between the two. And then here, knitting the actual material. So again, on these CNC machines, what was interesting, and the reason for working with knit, is that we can integrate all the detailing. So rather than having to sew all the pockets and so on for the channels to put in the fields, then we actually knit them into the textile directly. So a series of test pieces looking at this. we worked in polyester, high tenacity polyester. This is the actual developing of the knitting system and the testing of it. We tested we're doing this again right now, testing this knitting structure. There was no paradigms for doing this. All the textile testing is done on weave, and knit is much more stretching. So we had to sort of reinvent how you could even do this, and then integrating that into the machine, into the actual knitting. I'm a little bit sorry, my aim to be a bit fast, but maybe we can see it here. So what we're doing is that we're making all of these sort of pockets and reinforcements are built into the textile, and all the seamings, also eye holes to be able to sew the structure together. So this sort of integrated design, making multiple levels at the same time, has been really the interest of it. I'm not going to show this, I guess. And I'll say thank you very much.
We have time for a few questions.
Yeah.
Questions, please.
You have to go from listening to talking. It's always a bit hard.
I'm wondering actually, the animated model, I didn't quite get that. Is that the model where you integrate the different scalar considerations? Or is it, how is that done?
No, the animated model is simulating the relationship between the two. So I won't try to do that again, but it's actually simulating the relationship between the stiff member, which is in compression, and then the textile, which is in tension. And then what we're doing is we use the model. So here we're then sectioning the model into planar patterns, which are then knitted to shape. So we knit these patterns, we put all the detailing in, and then we knit them, and then we sew them together on site.
So imagine that the integration between the different scalar, I mean, you point that out, that is a major task. But it's still not quite clear to me. Do you model those things on their own, and then you bring them together, or do you actually create models where the integration of the interface between the different
So
scales?
it's a very large model which has a series of sort of shed lines between different processes. But the point is to have the feedback. So the main design model is doing the simulation to pattern cut, and then we have a separate model which is developing the actual knitting files. But the simulation to pattern cut is a very wide array already in one model.
Yeah, when you showed this data, I was quite curious to know how you work with the material information, like elasticity and tension and the twist of turning. How does that inform your parametric model while you're designing it?
Sorry, what projects?
Like the material information of data.
Yeah.
Do you incorporate it in your parametric system while it's designing to understand how it works? Because it's something that always is, either you model the geometry in the parametric system and you don't have so much of the material information.
Yeah.
And that material information affects the geometry substantially.
Yeah. So that's our research project now. That's the entirety of what we're doing, and we're doing it in many different ways in the different projects now. So we're trying to explore different ways, different methods of creating feedback between knowledge about the material system and the design system. And I think the methods that I have tried to show is things that are based on simulation. So we're integrating material simulation, which is this, for instance. Now you're simulating the bending of the rod, simulating the stretch of the fabric, and understanding how that's working, and then also understanding your design freedom. So it's a design tool. It's not something that's happening after. You don't design it and then simulate it, test it, and then build it. It's something that's happening together with the design phase. And then the sensing is the second strategy. And my main point is that these things are connected. So how do we, what's the information that's inside of our simulations? They're built on empirical data. We're testing things physically to be able to input the data into our models. And could we use sensors? And it's not a very strange idea if you look at sort of the way that motorways are constructed in, I'm always thinking of America, but sort of wide, if you have a big country, you have a lot of motorways, then you are, in the motorway bridges, you put in sensors in the corrugated steel to be able to track them, to see if they're corroding or something. So you're, in a way, you're sort of tracking your built environment. So these paradigms already exist, it's just that we don't know how to design with them. And I think the Curtin Project, where we're sort of Sifter, where we're trying to use the light sensors, is just a very early prototype of thinking, okay, well, how do we achieve, or how do we receive or gain data from the environment and then input it into the design environment, into the design tools to be able to then create site-specific materials. And of course it's a little bit heavy because what we're doing is we're creating a sort of curtain number one, it's a prototype curtain in which the sensors are sitting, and we're gathering data, and then we fabricate curtain number two, which is being put up. And there is something about the sort of strange sort of iteration of these things. But if we think in building life cycles, and that buildings are constantly being renewed in layers, so the life cycle paradigm, where you have different sort of, like an onion, you have different kinds of levels of how often things are being renewed, then maybe it's not so strange to think of, we could put sensors into our environment and then slowly ameliorate the way we're constructing our buildings. So I think that's the vision. What is this going towards? That we would build with greater sensitivity to our environment and to our use, so we, us, in this room, or also the environment for the building. Yeah, it's okay. No, I never even thought about making a simulation. Very interesting. Yeah, because it's such another category of projects is around actuation. But I think you're very right. It would be very interesting to simulate it. Right now we're with Billy Fairclough, who's the head of design at Kieran Timberlake. We're doing this project which is also looking at sensing integration into data. And then it's not in knit, but we're trying to work with these, the project I didn't show, SPIF, which is incremental sheet forming, where you're using a robot to press the material down. To use that together with wax, to use environmental impact, and then have so sun, so heat, and then the wax implodes and grows, whatever, swells and deflates. And so our interest is exactly to try to make coupled models. So I think the interesting thing in the multi-scalar modeling system is that you have a model of a big environment connected to the model of a small environment, material environment. But in this project here, what we're trying to do is understand how could we model the environment, like the site and the path of the sun and the environmental impacts within the material itself. And then understand how so a simulation of those materials. Hopping a little bit around it. It's very new, this project. But what I think it's a way, what you're saying, how do we simulate actuated systems within an environment, is what we're also trying to do there.
And also the system where it's not non-homogeneous.
Yeah.
Textiles that are non-homogeneous.
Exactly. Multi-material systems, I think, that's also what's important about Tower, is that, any architecture is multi-material, but a lot of these sort of material explorations in the digital culture and architecture are monomaterial. And I think what we're trying to sort of get into is understanding the interaction between materials. Yeah. But no, we never did that. But we just finished a paper that I hope will be accepted, but which was with a lot of our knitting collaborators. So Ayelet from Israel and also Jenny Underwood from RMIT. We also knitted some of these things on Dermoid. And there we looked at different simulation traditions coming from the different fields around us. So we have, of course, architecture and engineering, but you also have a lot of simulation in textiles. So you have simulation at both the user level and also at fabrication level, but also at gaming level. So there's actually a lot of very interesting cloth simulations happening in CGI. So we tried to sort of, I don't know if this paper will ever be published, but imagine it will be. Then what we're trying to do is sort of both create an overview, but also understand what are the differences, both in the goals, but also in strategies of these techniques.
Yeah, so I was wondering, during your introduction, you also mentioned the tapestries, which have a narrative that works independently of the structural logic of the textile. I was wondering, where do you see that in your work, or is that something that you're not interested in?
No, I'm super interested in it. I think it's the first projects that I showed with the curtain with the suction cups and so on, because of course it looks like a mountain range. I mean, very obviously, it's also called mountain curtain. But so it's sort of playfully siting itself within a space. It's a site-specific curtain. It is a curtain. It has a use. It has a particular performance. But it's also creating a poetic narrative that it's inserting into the space. So I think that they are wonderful stories, these sort of textile narratives and the richness of that culture. And what that sort of cluster of projects are trying to do is find ways of investigating that in our time, in our way. I think Petra Blaise's work is very akin to that.
I'm interested in the learning experience that you've made. Is that something that you keep using in other projects?
Yeah.
Was it a tool that existed and you adopted or you coded it yourself?
No, we coded ourselves, but algorithms exist, obviously. So they come from computer science. And we're right now working on it on the sort of inheritor project for a tower as a cable net. So we take away the knitted textile and instead we work with You're looking very nervous. I got scared. But cable net. So and here we're looking at what's really interesting about machine learning. I think we had a machine learning symposium this winter, and we brought a lot of people from many different fields: robotics, computer science, design, and so on, to come and talk about it. And I think. What I think is, we were always very curious about unsupervised learning, but I forgot the word, of course. But I think there's a guy called Kenneth Stanley at Carnegie Mellon who is interested in learning which is not optimization learning. So normally you do machine learning at something which is trying to optimize a particular protocol. But he's interested in making machine learning algorithms that are just novelty search. So rather than looking for something particular, which you define, and then you sort of make you give the algorithm a nice pat on the back every time it does what you want it to do, then it just says, oh, I reward you for every time you do things that are surprising. And then the idea is that through that we will gain knowledge that we were not aware of. So how do we know what we don't know, or how do we not know what we should, whatever, all of that. And I think that paradigm is very interesting for architects and designers because it's generative. So it's only Ken Stanley at Carnegie Mellon and novelty search. So one of the most interesting parts of this, to nerd away here, is they did this algorithm where they're looking at topologically different, so they're creating a genetic algorithm which is pairing topologically different structures. So if you sort of imagine you have one topology, and you have a very, very different one, normally you have to have topological asymmetry to be able to combine them. And so it's very exciting that you can combine,
So it would be a way of understanding the relationship between the three scales you mentioned, the macro, meso, and the micro.
Yeah, I mean, I think right now we're using it for understanding how we can do adaptive topology. So it's more around the question of parametrization. Yeah. Well, I want to say thank you very much for sticking in there.